Hello, everybody. Welcome to the 48th TrustML Young Scientist Seminar. So my name is Masashi Sugiyama. I'm chairing the session today. So today's speaker is Ryu Shu, the Gatsby Computational Neuroscience Unit. So he has been graduated from University of Tokyo 3 years ago. And then after that, he's in London now. And PhD student there. So today his talk is about learning deep feature in causal inference with unobserved confounder. Okay, Ryu, would you start?
Yes, thank you for the introduction. It's a great honor to present my work here as the former graduate from Masashi's lab. So following some peculiar convention, I'm not sure whether it is still there. Let me start with some catchy example of my work. So let's consider the following question. Does attending my talk increase the chance of publishing papers? Well, I hope this is true, but yeah, I hope this is true. The hypothesis is true. Like you can learn novel methods for causal inference by listening to this talk. I wish this goes without any discussion, but let's support this hypothesis by collecting data. So let's say, okay, by collecting data, we say, okay, we observe people who attend this seminar publish with 80% chance of publishing, and not attending people only publish in the probability of 72%. So okay, yeah, now the data seems the positive trends. So now the question I want to ask is, given these, should we force all researchers to attend my seminar? Well, if we force all AIP researchers to attend this talk, does that increase the chance of publication by 10%? Well, that might be less likely. So why that? Well, we're missing some hidden variable, which is known as confounder. So here, let's say here you are attending my seminar, and Y is the publication, and we have the really nice latent variable, which is your motivation, right? You have to be very motivated in order to attend my seminar, and also if you're a motivated researcher, you're more likely to publish in really good venues. So this variable, such as motivation, which affects both the treatments or action, like attending the seminar, and outcome, Y, the publishing, is called confounder. So this is the key of the causal inference. And what we really care about is the average treatment effect defined as this equation. So this intuitively means, what if we force everyone to attend the seminar? So here it is defined by integral of expectation times the marginal distribution of U, which means that no matter how much you're motivated, you must attend that seminar, and what happens to the expected outcome. Compared to the conditional expectation, which is defined as the second line equation, you can see that the distribution is now the conditional distribution of U given A, which means that if you're attending the seminar, you're more likely to be motivated. Thus, the conditional expectation may be different from the average treatment effect. So to correct this bias induced by this confounding is the key challenge in causal learning. And today's topic is actually more challenging because we're aiming to estimate the average treatment effects without observing confounder. Like measuring motivation quantitatively is super, vague, and it is really difficult to do that. So we want the method, so without access to this confounder, to get this average treatment effect. So this is not possible if we are not given any additional information, because conditional expectation is different from average treatment effect. So here we are considered some additional information to do this. Do you have any question so far? Like, is everyone here, like, with me to discuss this question? Okay. So just interrupt me when you have any questions. Okay. So today's talk covers the two methods. One is instrumental variable methods, which I always said IV, and another is proxy method. Which is proxy method, and these two are really related to each other, but IV assumes kind of specific form of confounding. I'll cover later, but requires the minimum additional information to get the average treatment effect. In proxy method, we do not assume the form of confounding, but requires extra additional information compared to IV. And also, we'll visit the connection between this IV method and proxy method to reinforcement learning, because this is, the causal inference and reinforcement learning are really, interconnected areas, and I want to show some interesting connection of these two methods to our real problem. And as the title says, like, we are trying to learn some deep feature in these IV method or proxy method, which enable us to the treatment can become the real high dimensional or even the structured image data. I'll show the empirical experiments on this, and we can learn the adaptive neural network feature from these treatments, which makes the strong empirical performance of the proposed method. Okay, so let's start from the IV method. The core assumption in IV method is the additive confounding, showing this first equation, where y is given as the average treatment effect, F0, plus some noise. So here the way of confounding is just additive, not nonlinear, just the linear one. And from the definition of average treatment effects, expectation of epsilon is always 0, but the expectation of epsilon given A is not 0. This suggests the existence of confounding, because otherwise, like, if this conditional expectation is 0, then if 0 equals to the conditional expectation of y given A, but that is not true in this case. And here we want to introduce instrument variable Z, which is which affects the A, the treatment, but not correlated with this confounder, which means the epsilon given Z equals to 0. So one potential choice in this motivation example is the time when the talk is scheduled. I guess it's 4 o'clock in Japan, but if the seminar is scheduled, like, let's say 7 a.m. in morning or 11 p.m. in night, you might be not able to attend the seminar, even if you're motivated. So this serves a perfect example of instrument variable, because that affects A, like whether to attend or whether to attend the seminar or not, but not correlated with your motivation. Do you have any question here for IV? Great. Then, given assumptions, let's see how to estimate the average treatment effect. Now, given these two assumptions, by taking the conditional expectation of Z, we'll have this blue equation for all Z. So we want the F that satisfies this. And hence, F0 can be learned by minimizing the disk loss. So which basically measures the L2 deviation of the both hand side in blue equation. And you can see that this loss is minimized if and only if that blue condition holds. And also their theorem says that F0 is the only minimizer of the loss if Z is sufficiently informative. So this is another hidden assumption in IV, because we need Z to be informative of A otherwise, like let's say z is just random variable, like you can see this doesn't work at all. So so they have to be sufficiently informative. But if that is true, f0 is the only minimizer of this loss, so we can minimize this loss to get the f naught. So now the question is how to minimize loss involving this conditional expectation. The challenge is that we have the conditional expectation inside the loss, so we want to decompose it. The one classic way of doing this is to consider the static feature map psi and consider the linear in-parameter model. So here we model the f to be the u transpose inner product of u and this feature map, and we want to learn the parameter u by minimizing the loss I have introduced that. Then from the linearity of the expectation, you will get this example. An idea is to estimate the conditional expectation of psi given z by doing another regression of z to psi. So this serves as the two-stage regression where, okay, let's say we have fa to be the linear parameter model. And also this conditional expectation is also the linear parameter model, where we consider another static feature map phi, and V is now the matrix. And then we consider, okay, in the stage 1 regression, we learn the conditional expectation of psi given z. So we learn V hats, the true weight by minimizing, the square loss plus some ridge penalty. And then in stage 2 regression, we learn the, weight u, which is what we want, by minimizing the loss I have introduced, but by replacing the conditional expectation of f given z to the estimation given in stage 1 regression. So V hat phi here, and everything is static, so we can we can get the minimizer of u by just solve the stage 2 regression. So this is kind of the classic way of doing IV method. And now we want to adaptively learn the feature phi by potentially by the neural network. So how can we do that? So here we consider the adaptive feature. So let's say the feature parameterized by theta, and potentially this can be neural nets basically. And we want to try to learn the u and theta by just minimizing the loss minimized by this IV loss. So again, the approach, we use the same approach where we replace this conditional expectation psi theta given z with the estimation of V hat, estimation of the linear function of the feature of the instrument. However, the problem here is that, okay, we want to replace the conditional expectation with this estimation. Then we're removing the information of theta, right? Because like the V hat is just the the result of estimation. So this is naively this is not the function of theta. So how can we do that? The idea is to use the closed form solution for V hat, because the stage 1 is actually the linear, the multivariate linear regression. So we do have the closed form solution for V hat, which can be used to minimize the second stage loss. Okay, so again, let's assume that FA is the linear function of the parameterized feature, and we assume the conditional expectation of psi to be the linear map of the static feature map. And then stage 1 regression, we obtain the V hat, which is the function of theta now, as the closed form solution of the same regression problem as the red equation, right? In practice, we just replace this population expectation to the empirical expectation, but we can analytically solve this closed form solution. And then in stage 2 regression, we learn weights and theta by minimizing the loss we introduced with replacing the condition expectation to the estimation given in stage 1 regression. Now you can see the closed form solution of V hat, which is the with respect to theta, the closed form solution of V hat is a linear with respect to the feature of the psi. So it is really easy to compute the back propagation, right? You can just back prop by just doing the by multiplying the inverse matrix of this one. And also I will not cover this in this talk, but we may learn adaptive feature for phi as well. So here I just give you the equation when the phi is static, which gives you a really simple closed form solution. But we may learn adaptive feature for phi as well by just so here we just alternate the optimization of phi and optimization of theta. So like once we update the theta, you update the phi, and then we go back to the updating theta. So that is how this alternative optimization works in empirically. And also we prove the consistency guarantee, which means that if every hypothesis space is correctly specified, our estimation of arbitrary band effects converges to the true one based on the Rademacher complexity. So it is really simple. So since the hypothesis space of your network scales as square root of n, so it achieves the parametric rate of convergence. Okay.
How do you handle lambda 1?
So lambda 1. Okay. So lambda 1 is the hyperparameter. Like I just use the same. Okay, that's actually a good question. Like because in causal learning you don't have any true target, so it is difficult to do this hyperparameter tuning. Our idea is like to use the stage 1 loss and stage 2, the held out data set for stage 1 regression and stage 2 regression. Right. So we use the held out data for stage 1 regression and select the lambda 1 to minimize that the stage 1 loss with respect to that held out data. And for stage 2 regression, we used lambda 2 to minimize this stage 2 regression, given the lambda 1 tune by minimizing the stage 1 regression. Do you get?
So when you show consistency, do you have to like shrink lambda 1 or lambda 2?
So here I show the consistency when lambda equals to 0. So
I see.
So I just assume Z is rich enough that this inverse is always full rank. So
okay, sure.
you can take the inverse, and so I just showed lambda to be, analysis assumes the lambda equals to 0. So that's one difficulty in.
Okay, thank you. That's clear.
Yeah. Okay. Do you have any question here?
Can I have a question in the former part of the talk?
What part?
Oh yeah, so my question is so about the instrumental variables. So I'm not so familiar with these fields. I want to confirm that. That slide would be good. So do you assume the availability of such Z instrumental variable? Sorry, let me rephrase the question. So in this field, the problem is to how to identify the confounder. And in the field of the instrumental variable, do you assume such Z is available in advance?
Yes.
So
yes.
I mean, yeah.
Mhm.
Oh, sorry. Yeah, let me continue
Oh,
a little bit.
yes.
So yeah, it is true that identifying the confounder is pretty difficult problem. I know it. So I wonder if the finding such kind of the good variable Z is equivalently difficult to the identifying U. So that's my question.
Yes, that is another very good question. But so there is in the real world application, there's several way to identify Z. Yeah, so that's true. Like but yeah, so in IV setting, like we assume that obtaining Z is much more easy to consider all the confounder of use. Well, that is something similar to, how can I say that? So for example, in the real world application in IV, one most famous one is that incomplete treatment, which is that you give you want to test the medicine, you want to test the effect of medicine, and now the A is of course the taking the medicine, and Y is the symptom, like the cure of the symptom. And here U is that, however, let's say that patients might be a bit lazy to take all the pills. Then the U is kind of industriousness of one patient, because like people who are not who don't willing to take the pill might be might be less educated and maybe have less chance of cure the diseases. In such a case, Z is our control, like whether to give the pill or not. Like so here the whether to give the pill or not is controlled by us, because like you can see that, and A is that controlled by others, have the control of the U. So like it is something similar to like incomplete random control test, which means that we can control some power of the treatment, but not entire power of the U. And we can use that power of control as the Z, so we can estimate the average treatment effect. Is that clear?
Yeah, thank you. Your example is pretty clear to explain my question. Thank you.
Yeah, so like actually this is really used in economics, and this is so famous that I guess the last year's Nobel Prize on economics is about this IV. So so I guess this is really have the good power of big power of a wide applications. Like at least they assume that.
Thank you.
So application IV is really nice. And also later I'll give the connection to reinforcement learning, which is naturally like this Z is coming from the Markovian characteristic, which is also a nice example of IV. Okay.
I have a question. Sorry. Could you elaborate the reason why the existing or proposed approaches, there are so many approaches based on the two-stage regression for instrumental variable regression, but I couldn't understand the reason why. So could you elaborate the reason, please?
Okay. Okay. So maybe just I'll just go to this this one. So here okay. So we want to learn the parameter U, the final weight, and the feature map psi, and we want to minimize the loss in the first line, right? But however, this expectation, the conditional expectation, is really it's not given to us. Like we have to estimate from data, and we cannot directly minimize f because due to this conditioning. So here our propose is that to, decompose, this expectation estimation and the weight by assuming this linear parameter model. And then we just estimate this conditional expectation first. And then the next, using that estimation, we minimize the weight minimize the weight minimize with respect to u. So that is two-stage regression. Yeah, so that's it.
So I couldn't understand. So I'm not sure about are there any other approaches to instrumental variable regression without performing two-stage regression? I'm not sure.
Yes, there is one another approach to do this, but and I'll come back to that later.
Okay, so then what is the advantage of taking two-stage based regression approach?
Okay, so I'll answer that when I introduce another approach.
Okay, thank you.
Okay, good. So so actually it comes really right after this slide. So here I just show you some experiments on the image data. I used the D-Sprite data sets, where which is really good data sets. It is originally proposed as the data set for kind of the disentanglement, which is that that is the image, the generated by 4 latents. The latents are the scale of the shape and the rotation, the angle of the shape, and the and the position of x and y of the center of the shape. And here I use the treatments to be this image and outcome as the quadratic function of this image plus some term with the position of y, so which is the confounder. And I use we use the instrumental to be the rest of 3 latents. And here I compare the 4 methods. The first one is DF5D feature IV, which is the proposed one. The second is the neural network feature. I just ignore the confounding, directly learns the y given x. The third one is kernel IV, which is that two-stage regression, where we don't learn the adaptive feature. We just use the kernel feature in this two-stage regression. And finally, that is the alternative approach to do this IV, which is called like general method of moments, which use the moment condition of y. So which is the moment condition of this y given x equals to f0 given x. Sorry, y given z equals to f0 given z. And we estimate f naught by solving this kind of minimax problem, right? So if y minus fx is not 0, there must be some g to to increase this entire loss. So by solving this minimax problem, we will get f that satisfies the condition of the IV constraint. So that is an alternative approach. And the advantage of this two-stage regression is that we don't have to solve this minimax problem. Like as in GAN, as you may see in GAN, like minimax problem is in general unstable to solve. However, in two-stage regression, what we solve is just to two minimization problems. So we don't have to do this maximization and minimization or like together. So this learning procedure is really stable compared to this method of moments technique. Do I answer the question like for this alternative method and advantage of two-stage regression?
Okay, thank you very much.
Are you happy with this? Okay, and of course I'll show you that the FIV performs better than this method of moments. Like since I'm advertising my paper. So so here I just use several training samples if of 5,000 and 10,000, and the mean squared error of the estimation is the best among other methods, where the NN performs the worst, of course, which ignores the confounding. The second to worst is kernel IV, because like the kernel feature is not good at image data, and then in the deep GMM performs the second to the best, and you can see that the variance is a bit larger than DFIV, especially in the case of 10,000 data, well, which suggests some unstableness of this method moment technique. Okay, and also as I told you later, so this has a really interesting connection to reinforcement learning, especially off-policy evaluation. So here in off-policy evaluation, what we're trying to do is to compute the Q function, which is the expected future return given the initial state at S and initial action to be A. So and this Q is characterized as the minimizer of the Bellman loss defined in the second equation, where R is a reward, and the Q is the Q function. And here and you can see that this really resembles to IV method loss, because it has the expectation in the inner loss, right? Because like it takes the expectation of the next state and next action of the Q, and then try to minimize with respect to Q. So which corresponds to the IV method loss, where sorry, I missed the notation here. X should be A. Sorry, the I mean A in the treatment to be the the set of like current state action pair and next state action pair, and Y is the reward, and instrumental is actually the current state action, and the average treatment effect is equal to equal to the Q function minus the the gamma times Q function of the next state. So this by using this interesting connection, we can use any IV methods to offline policy evaluation. And here we apply the IV method to mountain car problem, which is the challenging reinforcement learning technique. Reinforcement learning problem. And here we show that our methods works comparable to soda OP methods. Like so here DFIV is showed orange, and the blue one is the state-of-art offline policy evaluation technique, which is fitted Q evaluation. So yeah, so you can see that the FAV works comparable to that. Okay, so here is the kind of the overall topic for IV. Do you have any further question here? Great. Now let's move on proxy method. So as the question like asked, like assumption in instrument variable might be difficult to achieve, right? I told you that first we need the linear confounding, which is also strong assumption, where confounding is just affects the outcome additively, not non-linearly. And also again, instrumental must be not correlated with another confounder. If you do have the power of the controlling some treatment, then it is good. But as you can see, it might be difficult to find such instrumental as well. And the proxy, what proxy do is that it lifts these assumptions by observing additional variable. So we need to observe another variable, but we don't need to assume that confounding is linear, nor instrumental must be uncorrelated. So so this is the so we need, this is the kind of causal graph in proxy method. As you can see, we have another variable w here, and the key assumption is that w and z must be related enough to confounder, hidden confounder, and also z is independent of y given u and a, and w is independent given u, independent to z and a given u. So one a bit long example for this is that, okay, we want to assess the effects of, how much, how watching ads increase the chance of purchase. But, they still, of course, is influenced by the interest in cycling. And we may use the Z as the web access to the bike retailer, because if you're interested in cycling, you're more likely to access to the web page of bike retailers, and which increase the chance of encoding the ad. And we may use W as whether the customers go to gym to fit or not, which also reflects the interest in cycling. The people can exercise, like do aero bike in the gym. However, it is not, it is independent of whether one watching the ad or access to web, given the given how much one is interested in cycling. So that is, the view of proxy method. And there's one interesting theorem which states that given appropriate bridge function h, I'll give you what kind of appropriateness. We have that average treatment effect is the expectation of h given a and w, and we take the expectation only over w. So it's the partial expectation. And here, by doing this, we recover the intervention effect, which is, average treatment effect from the observable variables. And here, appropriate means that bridge function must satisfy the following equation. So expectation of y given a and z equals to expectation of AW given AZ, which is actually the same or really similar loss to insurance variable. As you can see that we can obtain the bridge function h by minimizing this loss. So again, this loss contains the conditional expectation inside the loss. So we can learn h in the same way as insurance variable IV. So here, let's say h is the linear in parameter model of the feature of a and w, and then in stage 1 we do the regression of the feature given a and z, and then in stage 2 we minimize the entire loss by replacing this conditional expectation to the estimation of the first stage. So that is really the identical trick as IV. And also, so we can learn. Okay.
Oh, sorry, I interrupted you. Anyway, so do we have to enumerate all the information regarding the W when we evaluate the bridge function? Or if we minimize this loss function LH, so we don't have to access any information of the W?
We need the W, actually. So here, sorry, the assumption of proxy is the we observe all the Z, A, Y, W variables. So we need these four pairs of data sets.
Okay, I got it. Thank you.
So now, like, it's really same as so now it's really same as the IV, because like IV have to observe A and Y and Z, and also in proxy we need to observe A and Y and Z and W. And then like you do this really the same trick on this loss. Okay. Okay, so I'm not repeating the slides to how to do this. Like, it's really same as the IV. And here, so again, I just set up one proxy method experiment using the dsprite dataset again. And again, the treatment is sprite image, and the average treatment effect is actually now the project function of A. But I omitted the equation from the slide, but we considered some nonlinear confounding here, so it is not it cannot be done with IV method. And I just compare to the other methods of this, like as I told you before, like because we're considering the same loss, there is also the way to do this with moment, like method of moment technique as well, but we perform better than that. And we show that our proposed method performs the best among proxy causal learning methods. And also we do some application to confounded bandit problem. So confounded bandit problem tries to learn, so what if we only showed ads to people who visit bike retailers? So here, the causal graph becomes there's no link from U to A, but we consider the new link like might be different from the original data, where Z to A. So given the original observational data of the original generated from original causal graph, we try to estimate the value function of some deterministic pi given Z, which is that we only show the ads like to the people who visited bike retailer website. And this value function is given as the expectation of this. And again, under some regulated conditions, we do have like we just replacing A to pi Z and take the entire expectation over W and Z, and it gets this value function given appropriate brief function, which is the same as the previous one. And so we show that proxy causal learning can be used in this policy evaluation. And I just we just create some synthetic data set for demand prediction for flight purchase, and now the treatment is the ticket price, and we want to determine the we want to determine the policy, which depends on the fuel price of the tickets. And then what if? So this corresponds to the problem of what if the ticket price is fully determined by the fuel price of the airplane. And again, we show that proposed method performs the best among PCL methods. Okay, so here's kind of the end to the talk. So in this talk, we cover the instrumental variable and proxy method, and which is given by minimizing the loss, where that loss includes some conditional expectation inside. And then we show some application of these causal methods to reinforce learning, right? IV can be used to offline policy evaluation. Proxy can be used to confounded bandit. And again, I show you that this advantage of the approach is that treatment, sorry, I missed notation again, like treatment A can be multivariate or structured image. And we can learn adaptive feature of X. And also, we have the strong empirical performance compared to other approach or other other method with the static features. Okay, so that's kind of the end of the talk. And do you have any question?
Okay, thank you very much. So are there any questions?
Yeah, I have a question.
Yes, please go ahead.
Thank you. Hello. So in the original proximal G formulas paper in 2018, I remember that the original paper also addresses not only unobserved confounder U, but also observed confounder. But in your causal graph, there's no observed confounder. So I'm not sure the reason why. So Can your method be applied with observed confounder? Is it possible?
That's a good question, and we do have that analysis. Do have that version of algorithm in our paper as well. So I just recommend you to check our paper. This deep proxy causal learning with application to blah blah blah. And we do have this kind of observable confounder as well. So here now if we do have the observable confounder, I forgot the equation, but I guess the H now take the arguments of observable confounder, right?
Yeah, exactly.
Yeah. So now we propose to learn the adaptive feature of D3, like W, A, and observable confounder. So we all use the neural network feature for D3 and learn the final weight as well. So that's, yeah. So I just omit that part in the talk, but yeah, you can definitely apply our method to observable confounder.
Is it very easy to extend your method to such kind of setting?
Yes, it's really easy. Like you just add one another feature to in your
Thank you
in your
very much.
regression. Yeah.
Thank you. Any other questions? Can you say a bit about computational issues? So do you have any difficulties in optimization?
Okay. So let me just go back to here. Let me just one. So basically, if we use the static feature in stage 1 regression, everything is really clear because not clear, but so the one computation issue is we have to take this inverse, and so it might be, and if we want to do the mini batch training, you have to increase the batch size because this expectation must be converged to the enoughly close to the true inverse. So you have to, so in the experiment, I don't use the batch learning. I use all data sets as one batch, and we are not doing SGD. But yeah, so that is one difficulty. And another is that if you want to learn the adaptive feature for the stage 1, you have to alternate the feature learning of psi and phi, which causes another computational difficulty, because better than minimax, solving the minimax, but still like this alternating procedure has another computational difficulty. The trick is that you need to update stage 1 feature more frequently than the stage 2 feature psi.
What was the size of V in the experiment?
V, so the matrix, right? So it is really small. It is because V is the dimension of the dimension of phi times dimension of psi. So this dimension is can be designed by us. So it is the output of the neural network. So it is fairly small. Like I guess I said 32 by 32 or something similar to that.
Okay, thank you. Any other questions?
So you mentioned those lines of the methods have a strong empirical performance, right?
Yes.
So can you just quickly summarize what is the main advantage, reasons why those methods have a strong empirical performances?
Okay. So one thing is that okay. So one is that we can learn adaptive feature in the second stage regression, which means that you can extract the feature, a useful feature from the image data. Like if we are to design the static feature of image, it is really difficult to do so by handcrafting. So which is the reason of the strong empirical performance compared to the method with static feature. And also you can do the method of moment technique to do that. Like it also can learn the non-linear neural network linear neural network model to, this average treatment effect. But again, the solving minimax problem is really difficult to converge. So, however, like our method only consider minimization, so it is more stable. The training procedure is more stable compared to other methods.
Thanks for the answer.
Further questions? Okay, otherwise, let's thank the speaker.
Thank you.
Yeah, today Liwan joined the session from London, so it
Yeah.
must be early in the morning for you.
Yeah, it's 8 o'clock, but
So
yeah,
thanks.
I'm the early bird.
Thanks a lot for the great talk.
Great. Yeah.
So
Thank
then
you.
if you have any further questions, maybe you can directly send an email to Liwan.
Yeah, I'm happy to answer that.
Okay, so that's the end of the seminar today. Thank you very much. Have a
Thank
nice
you for
day.
having me. Bye-bye.